Hello, everybody. So April 17th is now the first assignment in Unit 3, Chemical Reactions. So chemical reactions is this unit, and we'll be doing a variety of things that you have seen before, so we're not that unfamiliar with chemical reactions. So let's study double displacement reactions first, because they're the lab we're going to do. Essential questions. Why are the driving forces for a reaction to keep occurring? What are these driving forces that keep a reaction going until all the reactants are used up? And what are they, and how can you tell the difference between the two kinds of double displacement reactions? So double displacement are precipitation reactions and acid-base reactions. So those are going to be things that we'll use frequently. All right. So in the driving force, this is the definition of the word driving force, in a chemical change are the products that cause the reaction to keep going on until one of the reactants is run out. So examples I'm going to give in the precipitation and acid-base neutralization. One is easy to see, the other harder. All right. Whoops, let me fix this. There's some common driving forces that keep a reaction going. One is the formation of a precipitate, that is a solid, that when you pour things together, one of them isn't soluble, and so it drops out of solution to the bottom of the flask. And so that removes all of that product from participation in the reaction. So the reactions make more. Oh, this sounds almost human, right? As soon as I want some more product, so I just make some more. Then I make some more. When it's used up, I make some more. A second one is if you see gas bubbles. This is something we've seen a lot of. So when gas forms, we know that means it's leaving the solution, right, and going into the atmosphere. So the gas is no longer able to participate in the reaction because it's gone. It's gone out into the air. So then the reactants just make more and more. So every time you lose a product from the beaker itself, either dropping to the bottom or going up into the air, then you've got a driving force to keep the reaction happening. The reactants keep combining until there's no more. The third one, which is the acid base, is a formation of a covalent molecule such as water that doesn't ionize. So the H plus and the OH ions can't recombine after that. They are removed from solution, so the reaction makes more. So the key idea here is that when products are removed, the reactants keep making more products until one of the reactants is totally used up. All right, so this is the key idea. When we remove products, then the reactants keep making more products until one of them's been used up. So in the following reaction, you will be noting what the driving forces in each reaction, what the driving force in each is. That'll tell you whether it's a double displacement reaction or a precipitation, whether it's an acid-base neutralization. All right, so here's an example. I'm going to make this absolutely as big as I can. All right? Even to the point of, let's just do this. All right. You know what? It's not letting me change the size, so I'll do it like this. Sodium is dancing with sulfate on the reactant side. It says sodium and sulfate are dancing together. That means they're in a compound. All right? On the reactant side. But on the product side, so I'll put an arrow to show, the sodium is dancing with somebody else, with iodide. All right? I'll just put the bare bones here. And then barium begins with the iodide ion, so we have barium and iodine on this side. All right, and then, but barium on the other side is now dancing with sulfates. Ba. I'm just putting the bare bones together. I don't think those are the right formulas yet. I just know that that's what the sentence is saying. So do you see how I just did? I started talking in chemistry from a sentence expressed in English. Sodium is dancing with sulfate. Now I go up and I put charges. Sulfate. Well, sulfate is +1. Sulfate -2. So I know I have to have 2 sodiums. On the test, I noticed a lot of people were still very, very poor at doing this. You guys can't talk during the test?
I'm not taking the test. It's still downloading. Because Respondus is on my computer.
Because what?
Respondus is on. This is a new computer, so it's not on me.
Oh, okay.
I'm waiting for it to download.
All right, so Fernando, don't talk to it. All right. Now, barium and iodine, barium is +2. So you see how I said that if you didn't have these charges in your head by now, life was going to become pretty difficult, and the test showed that it did become very difficult for many of you. All right, on this side, we have +1 and -1. And on this side, we have +2. We already said barium was +2, sulfate -2. All right, so the first thing we have to do is get the right formulas. All right? Now, sometimes I'll be nice and give them to you, right? Like I did here below. All right, so the driving force for this reaction to continue is the precipitation. So I want you to go over here and see. Let's bring this guy somewhere where he's a little more useful. Let's bring him over here. Okay. All right, we had... All right, let me get over here again. All right, now here's the thing. Isn't one of the rules that all sodium compounds are soluble? All sodium compounds dissolve. So that means this guy is soluble. All right? But barium sulfate is insoluble. Yes, insoluble. So it forms a solid. All right, so the S stands for solid in the bottom of the beaker. So when we pour these two things together, what we get is crumbs of a solid in a beaker. And that's the barium sulfate. Now, the driving force for this reaction to continue is the precipitate that keeps falling out of solution. So removing a product causes the reaction to continue until either sodium sulfate is used up or barium iodide is used up. So this is an example of a precipitation, which is a double displacement reaction. Because sodium was dancing with sulfate, and now sodium's going to be dancing with iodine. Barium was dancing with iodine, and now is going to be dancing with sulfate. So we get the new partners are sodium dancing with iodine and barium dancing with sulfate. So it's double displacement. So double displacement means both means both metals get new partners. Means both metals get new partners. All right.
Unit 3.
Go up to OneNote.com. See if you see it there, and then download them again. All right. So this was an example of a double displacement precipitation reaction. The next reaction is also double displacement, but it's going to show you an acid and a base. You go to OneNote.com and then see if you see it up there, and then open it again in the desktop. Yeah, you can just do it right here. All right, now we're going to do an acid plus a base. Now these are the fun ones. All right, an acid. HCl. We already knew it was an acid, right? And it's going to dissociate into ions. And then sodium hydroxide, a base, is also going to dissociate into ions. All right? So essentially what we get here is a beaker full of H pluses and Cl minuses. And then what we have here is a beaker full of Na plus and OH minus, the polyatomic ion. All right, what they're going to do is exchange dancing partners. So hydrogen is going to be dancing with the negative one here. Sodium is going to be dancing with the negative one here. So we're going to get HOH, and water's a liquid, right? Plus NaCl, that is dissolved. So all sodium compounds are soluble, so there's no precip, is there? And it's water. Water's not a precipitate either, all right? So this is a double displacement without precipitation. Yeah, so. So you saw what you need, that you have the right program. Let's see unit 3. Yeah, all right. So what we're going to do is tell me what you want to do. And we'll put open. And then we'll open in the desktop. And that should, even if it still says it's a problem, it should appear. And there it is. Okay. Uh-huh. All right. So, it's just work. There, see, there it is. They had to go to unit 3. There.
I download.
Are you, no, you're fine.
But isn't that yours?
No. No, well, let's see. That should be. Oh. Oh. Are you saying it's not under yours?
It's not under mine.
Oh. There it is. There it is. So, Eddie, why does it keep doing that? Instead of going over here with you. Oh, is this, that's very odd. Let me see. Raise your hand if you have the April 17th assignment we're doing now. All right, so let me see if maybe the problem is that I think I sent it to you, but I didn't. I think that's the problem, guys. I thought somehow I sent it to you. All right, silly rabbit. Somebody here is a silly rabbit. All right, it's being distributed to you with the notes I already put on it. Yeah, being extra nice since it was my mistake. Uh-huh. And what we'll do, so you go ahead, it's not acting like it's going to allow me to, oh, it's still downloading. All right. So it's recording all of this. And so I was hoping all right. Okay. Anybody have it yet? So for those of you listening, the second hour people didn't have this, and I've been going on and on. All right, so now they're getting it with these notes already on it. All right. Raise your hand if you have gotten the assignment now. 1. All right, let me sync it again. All right. Okay, so here we got this. And then let me make the double wide product beaker. All right. So it's going to have HOH in it, which is not going to fall apart, and then NaCl, Na plus Cl minus. All right. So water is a covalent molecule. So let's draw something around it to indicate there ain't no way that's gonna ionize. No, water sticks together in water. Water sticks together. So when it forms, since it's covalent, it stays there. So that means the reaction keeps happening because water is being removed from the solution. So here's what this means. The driving force for the acid-base reaction to continue is the formation of HOH, a covalent molecule which dissociates into so few ions that we couldn't even see anything but 0 on distilled water. We know this because water has a very low conductivity. Yes, 0. We saw it, right? You heard that here, right? Removing a product from action causes the reaction continue, and in our case, this was the HOH. HOH is just H2O, correct? Yeah, all right. But you can see why I wrote it that way, because that's how it combined. This is called an acid-base neutralization. The pH of this one All right. This is pH 1. This is pH of 12. Oh, let's say 14. This is a pH of 7. So, the real way we can tell this is a neutralization, if we're not sure, is to do a pH test, right? I have some pH paper that it changes color depending on what the pH is. And then you can read the pH off of charts. All right, so be sure to put those pH amounts. Acids have a very low pH. Low pH. Bases have a high pH. All right, what do bases have? What kind of pH do bases have? A high pH. All right. All right, and then once they combine together, the OH part and the H on the hydrogen on the HCl combine to form HOH, and sodium is now dancing with chlorine. And there's no precipitate because this is soluble, right? So I put aqueous after it to indicate it's dissolved. All right, now balancing double displacement reactions. Oh my gosh. Let's see. When a solution of potassium hydroxide, all right, see how we're translating from English into chemistry? Combines with a solution of iron 3 chloride, FeCl. Iron 3 means this is plus 3, negative 1, so it means we must have FeCl3. What are the products of this double displacement reaction? Well, we're just exchanging dancing partners, correct? Correct? So everybody needs to be looking at my screen off and on, unless you're taking the test. All right, so potassium's going to be dancing with chlorine, and we just write whatever it is. We don't take this 3 because chlorine is not going, there are not going to be 3 chlorines over here. There's only going to be 1 because potassium chloride, they each have the same numbered ion but opposite charges. And then iron is going to be dancing, and this is iron plus 3, is going to be dancing with hydroxide. All right. And since this is negative 1, and that's positive 3, I know FeOH3 is going to be the right formula. All potassium compounds dissolve, so I know this is aqueous because it dissolves in water. So remember that AQ stands for aqua, and agua comes from that, which means water, dissolved in water solution. This guy, though, many hydroxides are not soluble. So let's go check out iron hydroxide. Here's hydroxide. Iron. Oh, insoluble. Insoluble. Look. So that means it's going to precipitate out if it doesn't dissolve. So that means it's going to be a solid in the bottom of the container. All right? It's a precipitate. Just a second, let me go down here. Oh. So when we balance equations, we do so to fix things. So let me get a different color. Let's count atoms. All right, so we've got the correct formulas. So the first step is to correct formulas. Now we saw that hey, all right, let's count metals first. Potassium. So how many potassiums are on the reactant side? Abraham. Oh, you're taking the test. Aaron, how many potassiums are on the reactant side? These are the reactants. How many atoms are there of, or ions of potassium? Well, how many does it say? KOH. Just one. All right, and we're going to treat this whole guy as one. All right, let's count irons next. So usually we do. So Aaron, how many irons do we have? Yeah, just one. Then we go back and we count the polyatomic ions or the nonmetals. How many, Aaron, do we have of chlorines? So this right here means 3 chlorine ions. All right, and then how many hydroxide ions? We keep polyatomic ions together. 1 OH. All right. So the conservation of matter says there should be the same number of each kind of atom. And over here we see we have 1 potassium, 1 iron, 3 hydroxides, and 1 chlorine. Oh no. Oh no. What's the problem, Aaron? I'm sorry? Do we have the same number of atoms of each kind? No, we don't. We have 3 hydroxides and we have 3 chlorines. So I'm going to have to put a 3 in front of the whole molecule. That's called coefficient. Now we have 3 potassiums and 3 chlorides. Oh shoot, you know what? Now we have 3 potassiums on this side, but we only have 1 over here. So I'll have to have 3 potassiums. Now we have 3 potassiums and 3 hydroxides, 1 iron, and 3 chlorides. Over here we have 3 potassium, 3 hydroxide, 1 iron, and 3 chlorines. This is now balanced for conservation of matter. Once you know how to build correct formulas, I usually space this out. And now we're going to be balancing the number of atoms for conservation of matter. That's what balancing does. First, you have to have the correct formulas. And so the coefficient in front of this would be 1, right? There'd be 1 of those, and there would be 1 of these. All right. So we just wrote an equation, and then we balanced it. So the first step is correct formulas for all the particles in the atom. And the second is counting up the number of atoms of each kind so that you have the same number of each kind of atom on both the reactant side and the product side. Once we've done that, it is balanced. We have balanced the equation. All right. Now let's go down here and do the next one. Hydrochloric acid, pH 1, is combined with sodium hydroxide, pH 13. All right, write this reaction, their states of matter, then balance the equation. All right, go ahead and do that. Acid. All right, you go ahead and do that. So the sentence in English tells you what to write. So the acid and the base are both aqueous because they're dissolved in water. So you should have hydrochloric acid plus sodium hydroxide forms HOH, water, plus salt, NaCl. All right, so see if you got that correct. Did you get that equation correct? So you need to be able to write these now. Both the acid and the base are aqueous. We've only been talking about aqueous acids. Or aqueous, or aguas. And so there's an exchange of dancing partners. All right. Where hydrogen is now dancing. Whoops. Let me erase that. And get a darker color. Okay. So hydrogen is now dancing with hydroxide, and sodium is now dancing with chloride in the exchange of dancing partners. So we have this reaction written. And this one would keep going because water is forming and it's covalent. And so it does not break apart into solution. So essentially this guy eliminates himself from a solution by not ionizing. Whereas sodium chloride is an ionic compound. So it immediately dissociates into plus and minus. All right, now let's balance this guy. Let me get my red pen. Well, I only see one hydrogen and one chlorine over here. I see one sodium and one hydroxide over here. You can see why we want to keep hydroxide separate, because it makes balancing a lot easier if you do it by polyatomic ion, if they're both on the same side. So here we have one hydrogen and one hydroxide. And here we have one sodium and one chlorine. Did you notice that we have one of everything? So therefore, this is balanced. This is a balanced equation. Once we wrote the correct formulas, we had a balanced equation. All right, now aqueous nitric acid is mixed with aqueous ammonium hydroxide. Write out the products of this double displacement. All right, let me get another color. All right, so it says aqueous nitric acid. Nitric acid is like hydrogen nitrate. All right. And it says it's aqueous, so I know I put AQ after it. Says it's mixed with aqueous ammonium chloride. When I look on the polyatomic ion chart, ammonium is the only positive polyatomic ion that we use. And it said the other is OH. All right. And then we just exchanged dancing partners. And here we go. So hydrogen is now going to be dancing with hydroxide. And nitrate is now going to be dancing with ammonium. So we end up with HOH again. Oh my gosh. Water seems to be formed in every neutralization reaction. Oh my gosh. And water, of course, is in the liquid state. And then NH4 plus is going to combine with NO3 minus 1. So minus 1 and plus 1, we've got the correct formula. Now I'm going back to negative 1, positive 1, negative 1, positive 1, just to make sure I have the correct formulas. This is aqueous, all right? And this is aqueous. Aqueous is a state of matter in a chemical reaction. It means dissolved in agua. Now, balance that equation. Start counting. Let's see what we got here. I see one hydrogen and one NO3. Since we have NO3 here, right, and NO3 here, I'm just going to count polyatomics, because who wants to break the nitrogen and oxygens apart and count them separately if you don't have to? And this has one NH4, same idea, and one OH. So I don't want to separate them. If I see an OH on the other side, there's one hydrogen plus and one OH minus there, and one NH4 and one NO3. So do you see how it's kind of laborious at first, but actually, after you do this a while, you can think it in your head. So, Mark, do you think this equation is balanced as is? What do you need to fix? What is there not the same number of? I'm sorry? Well, then count. All you have to do is count. Look up there. There's one hydrogen, one nitrate. Look on the other side. Is there one hydrogen and one nitrate? Yeah. See, it's right here. Okay. Then this has one ammonium and one hydroxide. Or is there one hydroxide and one ammonium on the other side? Yeah. Well, all right, take those earphones off. I don't want to see them ever again. You're not paying attention. That's unacceptable to me because you're not testing, right? All right. You need to know how to do this. All right, so this is balanced, and it means the coefficient is just 1, right? 1. 1. And if the coefficient is 1, we don't have to write it. All right. Now, the next one is an acid you're less familiar with because it is sulfuric. It's like hydrogen sulfate. So, hydrogen sulfate would be HSO4, correct? Sulfate has a -2 charge. Hydrogen has +1, so we know there's going to have to be 2 hydrogens in this correct formula. So it says aqueous solutions of acid and base are mixed together. The acid is sulfuric acid. The base is potassium hydroxide. All right, both are aqueous. So we're going to add them together. Potassium hydroxide is the base. Hydroxide -1, potassium +1. Hey, we have the correct formula. All right, now we're just going to get an exchange of dancing partners. So write who those products would be. Who would it be with the exchange of dancing partners? Where the positive guy in one is now dancing with the negative in the other, and the positive in this guy is dancing with the negative of the other. So hydrogen is dancing with hydroxide. There's water once again. And who's the other guy? The other guy's potassium, SO4. All right, we don't transfer any subscripts because we have to reform them on the other side based on charges. Sulfate is -2, potassium +1. So we know we need 2 of these. All right, this is in water solution. All potassium compounds dissolve, so I know that's that. Water is the covalent molecule. All right, -1 +1. That's the correct formula for water, and water is just a liquid, right? So now you're going to have to balance this one. So we'll have to count. So you start counting over here on this side. All right, so I see this 2 right here says that there's 2 hydrogens. All right, and 1 SO4. We only have one of the SO4 groups. The other side has an SO4. That's the reason I can keep SO4 together. With KOH, there's one potassium and one hydroxide. All right, did you see that? All right, now we'll go over to the other side and count. We have one hydrogen and one hydroxide. Here we have two potassium, but one SO4. All right, now let's look at both sides and see if they match. Oh, look, this side has two hydrogen right here, but the other side only has one hydrogen. So what we're going to have to do is this. We're going to have to put a 2 in front of HOH. So that means now we have two hydrogens, but that also means we have two hydroxides. All right? All right, we already have two potassiums and one sulfate over here. Two hydrogens and one sulfate. Whoops. Let me see. Are we okay? Let's put them together. All right. KOH. Oh no, there's two potassiums. So now we finally get the two potassiums we need to match the two potassiums here. All right. These two. And now we have two hydroxides to match these two. All right, so it is balanced. 1, 2, 2, 1. All right, class, finish the rest on your own. I'll talk to you later. Bye.